for anybody not here. And then let's see here. Are you seeing you're not seeing my screen yet though. I am recording. So now let's present my screen of where we're at. Okay, so we're going to start looking at beam deflection here. And this is a lab. We are going to be back in school next week. So we're going to be able to do the lab part of this assignment next week. And it probably takes about 2 class days. And I've got all that set up and ready to go. For today, we're going to be able to do question number 5. So we're going to kind of walk through the PowerPoint and look at how we use this formula and what we're talking about. And then we'll look at question number 5 in this assignment. This is the entire lab. We'll just work through number 5. And we'll do a couple of those together. And then you can work out the other ones on your own. Okay? Let's see. So if we look at going through the PowerPoint, okay, this is introduction to member properties. So the one property we looked at earlier this week was the centroids. And now we're looking at moment of inertia and beam deflection. Okay, so a moment of inertia, if we have those two boards, it's the same exact plank, but which board is going to bend more? Anybody out there? If we put a weight on those, which one's going to bend more?
B.
Yeah, B is going to bend more. Just, you just take a ruler and you put it on end. You can't bend it, but you can bend it the flat way. So B is obviously going to bend a lot more, and that is the moment of inertia. Now, I don't know where this formula came from, but whatever it is, the orientation of your beam makes a difference. And that's why, that I-beam is a very lightweight structural piece, but that moment of inertia is base times the height cubed divided by 12. Now, this doesn't have... This would get a little bit more complicated than if we had an I-beam as a part of this. We're only going to do moment of inertia and beam deflection with a straight rectangle. We did central, so it would be similar, and that I-beam would be stronger than something else for the weight that you have. So again, what do you got to do? All you got to do is plug those numbers in. It's this base times height cubed divided by 12 is the moment of inertia. So that moment of inertia ends up being 21. If we flip the beam over, now the height is only 1.5. So base times height cubed divided by 12 is only 1.5. Okay. So, and when we look at those, that means that 21 divided by 1.5, it's 14 times stiffer. Okay. So that's the first concept that we're going to kind of look at. Moment of inertia. If you have your formula sheet, we are going to need that formula. If you don't have it, we'll write it down. But these formulas are on your formula sheet, and there's a whole section on beam deflection. It's also the same formula sheet used for CEA, civil engineering. So we're only going to use the simplest version for POE. Okay, so obviously, we could do more complicated moments of inertia, and notice that the I-beam is almost just as strong as a solid beam of the same size, and it also has a lot less weight. So that's one of the things that we do. The material also makes a huge difference. Is it plastic? Is it steel? Is it wood? And, the moments of inertia are going to be the same, but then materials have a property called the modulus of elasticity. And, modulus of elasticity is how well does it stretch and how strong is it, how stiff is it, and that's based on the material composition. And modulus of elasticity is usually a number in the millions when you start working through things. So here's the overall beam deflection formula. In fact, I'm going to copy this over so I'll have it to look at when we work out a couple examples. But we have force times whatever the force is, times the length of the beam. So the longer the beam is, and we think about this with bridge pieces, that's why we put triangles in there so you shorten the members. The length of the beam cubed divided by 48 times E, which is the modulus of elasticity, times I, which is the moment of inertia. Okay, so once we have all that given information, you have to find it. And again, Doug Furr has it's a number in the millions, 1.8 million PSI. And ABS plastic, we know plastic is not as stiff as wood or aluminum or steel, is only 419,000 PSI. So if we look at that, the beam, if we put this beam up on end, now the one thing about this, length always has to be converted into inches. So even though the beam is 8 foot long, we have to change 8 feet into inches, which is 96 inches. And then the moment of inertia is calculated, the load that you put on it, and then that gives you, it's only going to deflect, if you put 250 pounds on it, it's going to deflect 0.12 inches. And on the plastic beam, it's going to deflect over half an inch, 0.53 inches. Okay, does this kind of make sense, guys? So nobody's answering.
It's making sense to me.
Making sense to you? Yes? So let's see. I can't, oh, there we go. Let's extend this page. So there's beam deflection. And let's see, what's our other formula? Let's grab our other formula from over here, moment of inertia. Okay, so if we look at, let's just work through number 5, and we usually do this as a summation, but since, you know, it takes 2 people to read instruments and walk through the lab, we can't even really start with the lab. What do we have? A common 2x6, which a 2x6 actually is not 2 inches by 6 inches, it's 1.5 by 5.5. So let's look at what we know here. What do we have? 250 pounds of force. So we have let's see, I had to walk up front. We have 250 pounds of force, and our modulus elasticity is 1,510,000 PSI. And the span is 12 feet. So we are spanning 12 feet. But that 12 feet is actually, let's see, 12 times, what's that, 144 inches. Okay, 12 times 12 is 144. And then we have a couple different structural members. So if we take the 1.5 by 5.5 and we orient it vertically, okay, then let's see, that moment of inertia would be 1.5 times 5.5 cubed divided by 12. Okay, anybody have their calculator handy? .5 times 5.5 cubed divided by 12. Anybody get an answer?
I have 20.797.
Okay, we can go 3 sig figs, so 20.8. Okay, and the units on that would be inches to the 4th power, because we have inches times inches cubed, so that's inches to the 4th. And then, so what's the full deflection? That's what this delta max is. That's the amount of deflection. So that would be the force, 250 pounds, times the length cubed, which is 144 inches, and then we're going to cube that, divided by 48 times the modulus of elasticity of 1.5 million psi times the moment of inertia, 20.8 inches to the 4th. Now, if you're going to enter all this in your calculator in one step, you need an extra grouping symbol right on your doing your division. So we got 250 times 144 to the 3rd power divided by 48 times 1.5 million times the 20.84. Okay, anybody get an answer for deflection?
Wait, 495.
Yeah, I'm getting 0.49. I guess I got 0.494. I'm not going to get excited about that. One of us might have a small typo somewhere. Okay. How does that change? I guess we could answer, what is 1.5 times 5.5? The cross-sectional area, whoop, not sure why that jumped on me, is 8.25 square inches. And that's the same on both of those. How does that moment of inertia change if we do the same board size horizontally? Okay, come on, computer, extend the page. There we go. So if we do that beam horizontally, then we would have what? We would have 5.5 times 1.5 cubed divided by 12. which is what, 1.54? 1.55 if we round. Okay, so then how does that then change the beam deflection? So then the beam deflection, everything's going to be the same. 250 times 144 divided by 48 times 1.5 million times, the only number that is different in the whole equation is that moment of inertia, which would be 1.55.
And 144 is cubed, right?
Oh, yes. Good catch there, Daniel. I want that length is cubed. I would have got an answer that would have been way too small if you wouldn't have caught that. I would have caught my mistake here in a second, but so then what are we getting? Everybody get an answer?
6.64.
Yeah. 6.64 inches. Okay. So really, that's pretty straightforward. You want to do one more together, or you think you got it, guys? The only thing that's changing in the whole problem is now we're changing our sizes for the other two. Wow. Anybody want to do one more? Or do you think we got it? The only thing that's changing it for all of them is our moment of inertia and which way we're orienting the beam. Nobody's answering. You want me to do one more, or are you good?
We can do one more.
You want to do one more? Okay, we'll do one more. Okay, so now instead of a 2x6, we now have a 2x8. Okay, so this would be a 2x8, but then so the area is actually only what? The area would be 1.5 times 7.5. Which is 11.25 square inches. And that doesn't matter, orientation on that doesn't matter at all.
Wait, is it
Moment of
7.5 or
inertia.
7.25?
Which is it? Is it
I
7.25?
think-
Oh, good call. Ah. I'm glad you got out of bed this morning. That'd be Laffy Taffy if we were here in the classroom. You catch the teacher making a joke, isn't that, or making a mistake, isn't that a Laffy Taffy? So let's see, then the moment of inertia in this orientation would be base times height cubed, so that would be 1.5 times 7.25 cubed divided by 12. Anybody got an answer for that?
$47.6.
I'm getting 47.6. And I guess if we go horizontal, we get what, 1.5, well, it'd be 7.25 times 1.5 cubed divided by 12. We get 2.04. Now, the other thing is, you know, even though we're kind of working these things out, one of the features that Inventor has that Fusion does not have, Inventor would let you set up and actually do this experiment. If you know the material property, that modulus of elasticity, that E value, that is Young's modulus, and it is in the materials properties. And you can actually set up and put a force on, and the computer will model it, which is really kind of awesome. Fusion does not have that capability. They do have in the materials properties, when you pick your material, it will reflect that, hey, we have this material and it's modulus elasticity, but they don't have the stress analysis built into the program yet. I don't know if that's something that would be coming or not. I would see down the road it would be. Anyways, what would our deflection be then? Our deflection, we've got the force of 250 pounds times the length cubed, 144 cubed, divided by 48 times E, which is 1.5 million. Times our modulus elasticity, which, what are we getting, 47.6. Everybody get an answer?
Yeah, 0.216.
Yep. And then for the other one, the only thing that will be different is that moment of inertia. Which is what? 2.04. So we get, I got
5.048.
Yeah, 5.05. Who was that answered? Is that Sophia?
Yeah.
Okay. All right. So that gives you got one more question to do. And then when we're here next week, we'll actually stand on the board. What we're gonna do at the beginning of the lab, I guess I'll scroll back up. It actually is a fun experiment. We have a board. They tell you the curriculum says to use a 2x4, but as you see from those other things, if you use a 2x4 and put it flat, you basically would bottom it out and it would end up sitting on the ground. So, you can't put it up high enough. So I've got a piece of maple, and I actually built something so we can do this experiment safely. But we'll actually figure out the modulus of elasticity using my weight. And then using that modulus, you'll be able to predict your weight and see how close you could get with your weight by taking the measurement of how much the beam deflects. So it's actually kind of a fun activity that we'll be coming back to school to do. Okay. I'm going to stop recording.